Am I audible?
Yes, yes,
Right.
yes, audible.
Just give me 1 minute. Huh? I'll be back. Just 1 minute.
Yeah, sure. Yeah,
Okay.
now it's better.
Uh-huh.
Now it's better.
Yeah, I got my camera.
Okay.
So I have the laptop camera is not that good.
Mhm. So we will start in 2-3 minutes, sir.
Sure, sure. So how is it going?
Yeah, it's
In the
going well.
direction?
Yeah, just now around 5 sessions are over. This is
Okay.
sixth session. So one session today morning we had on ethical hacking. So he's a ethical hacker. I mean, well-renowned ethical hacker, Sai Satish.
Okay.
So yeah, he gave the first session, and the second session we have from Dr. Satya. He is working at Citibank, Ireland. So he gave
Okay.
talk on advanced persistent threats.
Interesting.
Yeah.
Yeah, program was nice. There's a lot of breadth, which is
Yes. 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 Also, we discussed a few basic thing also because everything we need to cover. So one session I dedicated for cryptography basic things, and then rest all are some research directions people are discussing.
okay. Okay. Good.
I hope you can share your screen also. The option
I'll
is
share. I'll just share it. Right. Just give me one moment. I'll just share it.
yeah, it's visible.
It's visible, right?
So yeah, so we will wait for 1-2 minutes, then we will start.
Sure. Sure.
Yeah. Okay, so let's start the session. So very good afternoon to all the participants. For this session, we have with us Dr. Dhiman Saha as the expert speaker for the session. Before he start his talk, let me take the privilege to introduce him. Dhiman Saha is currently working as an assistant professor in the Department of Electrical Engineering and Computer Science at IIT Bhilai, where he joined in 2018. He is also associated with Bharati School of Telecommunications Technology and Management, IIT Delhi, in the capacity of adjunct faculty. Prior to joining IIT Bhilai, he was a visiting scientist at RC Bose Center for Cryptology and Security, ISI Kolkata, and a research associate at Crypto Research Lab in the Department of Computer Science and Engineering at IIT Kharagpur. He received his PhD in 2017 from the department, with broad area of research includes both theoretical and physical aspects of cryptography. As a part of his thesis, he worked on the cryptanalysis of hash functions and authenticated ciphers. He has been involved in the analysis of the latest cryptographic hash standard, that is SHA-3. Before joining his PhD, he worked in the electronic design automation industry for over 2 years. He completed his MS degree from IIT Kharagpur in 2009 with a thesis on hardware security. He received his BE from NIT Agartala in 2006 and was awarded the gold medal for computer science and engineering. He was also a recipient of NEC scholarship during his BE. His research group at IIT Bhilai, known as Deciphered Lab, focuses on both theoretical and practical cryptanalysis and also on aspects of system security. His current research interests are lightweight cryptography, symmetric key crypt analysis, and fault-based attacks. So with this small introduction, I hand over the session to Dr. Dhiman.
Thank you, Sanjeet. Thank you so much. And welcome you all. First of all, I would like to thank Sanjeet for organizing such a faculty development program. I think these kinds of programs are very much important for us. And mostly security is something that is not compromisable, right? No one would like to be 80% secure. We want to be 100% secure, right? Of course, some people would say 100% security is a myth, but let's not go into a debate. So I think this is a very nice time to have this FDP, and I think you guys are learning from all the different experts. Today's the session, as Sanjit has mentioned, is on lightweight cipher design. Now, I have some assumptions that you guys have had some basic introduction to cryptography, so probably I will not go into that. But at the same time, this topic, lightweight cipher design, will need some kind of involvement. So there will be some theoretical part in it. So I hope I'll be able to, bring the point home. So if you have any issues and understanding something, don't hesitate to stop me in between, and we can discuss. Okay, and I'll try to see how I can give you this flavor or this kind of cryptography. So, as already mentioned, we are talking about lightweight cipher design. Now, before going into lightweight cipher design, what we will do is that we will look into what a cipher design is in general. Okay, and then we'll try to see how we can make it lightweight. And first of all, if you go to a gym, you understand what lightweight means. There's a single definition to that. But when it comes to cryptography, there is no single definition of lightweight. So there are multiple flavors, multiple dimensions to this lightweightness, and that is what we will try to uncover today. Look at various dimensions and try to understand how it helps us in identifying what it means to be lightweight and how to achieve lightweightness in general. And we'll start with a fact check. Okay, so why are we moving towards lightweightness? That is a question. That is, I think, perhaps the most basic question that we can have, that why are we trying to move towards this lightweightness? And this fact check actually tells us a big story, a bigger picture, that almost 98% of the manufactured microprocessors now utilized for embedded systems, and only 1.2% are utilized for traditional systems, right? This was not the thing, I think, at least 10 years back also. I don't think we would tell something like that. So we are increasingly moving towards something that is more mobile, right? We are looking for mobility, right? And hence we have this kind of systems. And as the new terms have come, right? We know about the Internet of Things. In fact, we also know about the Internet of everything, right? So it seems that everything that is there will have two things that are needed, to make it so-called smart. That is, one is connectivity and it is computing power, right? So if we put these two things to any device, anything there, anything under the sun, right? We put these two things, add these two functionalities, then we make it connected to the internet, right? And it kind of lives there in the Internet of Everything. So with this being the picture, security also comes into in a very large way, because as they say that a system is as secure as its weakest link. Now, if you have a smart bulb and you have connected it to your Wi-Fi, okay, and it's that bulb, then it's an issue, right? You might think, okay, what is a smart bulb? Why we need to have so much security built in? But that smart bulb can become the weakest link, and hence compromise the entire system, the other parts which you have, which you hold dear to yourself. So this brings us to the context. We're trying to set the context here, right? So in terms of computing, if we look into it, initially we had these mainframe computers, right? I think some of you might here have seen that. Mostly it is the earlier generation of us that had mostly contributed to this kind of computing, whereby they used to have this on a single machine, and many people would use that machine, and hence they would have queues. Nowadays, the thing that we face for high performance computing, if you need to get access to a supercomputer, you need to be in a queue. You submit your job in a batch, and then the scheduler will schedule it, right? But there was a time when even the regular computing used to be like that. So that was the time of mainframes, when you had this one-to-many relation. So there is one computer and many people trying to use it, right? And then came the age of personal computers. I think we all are witness to that. The age of personal computers is when we had one-to-one, right? All of us had our PCs or laptops, or that kind of a setting. When we could use a single machine, single user systems, we will use them together, right? And then, of course, we are also witness to the mobile revolution. And we know now that we have maybe multiple smartphones in our pockets now, right? And hence we have this now relation that we have multiple computing devices in our hands, right? So this is already there. We are already living that thing, okay? And as 5G and other kind of next generation technologies are coming in, and with the cost of computing becoming very less, and that cost of data access becoming very less, we are already in line for the world of pervasive computing. Okay, like computing everywhere, everything that there is has a computing power, right? So there's the many-to-many relation, in like which we again can mention in the term of this Internet of Everything, or whatever you want to call it. Okay, so we have the many-to-many. So the computing bandwagon has moved from the earlier times of mainframes to the current times of many-to-many. So it's a mesh. It's everyone connected to everyone almost in that setting, in some hops. Maybe not directly, but in some hops. So with this, we actually come to a stage where you would like to define that what means or what amounts to LWC, or lightweight crypto, okay, in terms of the device spectrum. So if I try to refer to this NIST report by Meltem and Nikki Muhua and Macquarie. So this report on lightweight cryptography, so I think NIST, you guys might know, it's the National Institute of Standards and Technology. It's a standardization body in the US, which is actually responsible for many international competitions that have happened in cryptography, like the AES competition, the Saha competition, and latest two competitions are going on. One is on post-quantum cryptography, another is on lightweight cryptography. So according to them, according to their definition, which I think most of us would agree, okay, is that servers and desktops and tablets and smartphones, this fall in the category of conventional cryptography. Okay, conventional cryptography means cryptography that is general purpose, that is not tailored for something. While if we look at the other end of the spectrum, we have embedded systems or this radio frequency identification RFID devices or sensor networks. Okay, these kind of devices like simple IoT systems like Raspberry Pi or very simple or even more simpler than them, even more restricted in constraint in terms of computing power than them. Those fall in the device spectrum of what we like to refer as lightweight cryptography. Cryptography that has to be tailored for a special type of devices because they are constrained in some way. They may be constrained in various ways, like their power may be less. They may be running on battery, hence they have to be power efficient. They may be, constrained in the in terms of, what can I say, like area. They're very small. They are living. Maybe it's like some kind of a button on our shirt that has a computing power. Okay, maybe we don't know. It may be some kind of sensor. The button senses something and does something. We want to put sensor in everything nowadays. So that might also need some kind of security. And then, as I mentioned, our smart bulb, our smart watch, anything that has a smart dot star. Okay, the regular expression I guess I can use. So there we need, perhaps we will be needing this lightweight cryptography, and that's the basic setting of where lightweight crypto comes in for resource constrained devices. Now this resource can be anything, and we'll quantify, we'll try to see what this resource means. But this is the basic setting of what amounts to lightweight crypto. Moving on, I like this picture. I have specially chosen this for this particular context of lightweight crypto. So why lightweight crypto, right? See, the idea is, like this picture tells us from this movie, that if we try to pull off something bigger with smaller resources, we might end up getting in some kind of a bottleneck. Okay, because not everything is meant for everything. Now, when we have designed cryptographic algorithms in the past, we did not consider that they'll be running on some smart bulb, okay, which will be highly constrained. Okay, or maybe running on some sensor which is in the ocean, measuring some temperature, that is maybe solar powered, hence very less power it can have. And hence its computational complexity and the computational power, they are to be taken into account. Okay, but when we have designed ciphers in the past, we never took those into consideration. Hence, if you try to run conventional cryptography or conventional cryptographic algorithms for lightweight devices, for devices that are resource constrained, then you'll end up like this picture, end up being bottlenecked or being starved in terms of it will not be a normal thing. It is going to have an issue. So this picture kind of sets the tone for this kind of crypto, right? Now the next thing that comes into the picture is that how do you quantify lightweightness? So as I mentioned, this I think is one of the most important series of slides that we have that are coming up, is to understand what lightweightness is. We have to quantify, and we have to quantify this in terms of hardware and software, both the perspectives, both hardware and software perspectives. Because when we design ciphers, we may not design them keeping everything in mind. They may not be general purpose. A cipher may be designed keeping in mind the dedicated hardware, like application specific integrated circuit, ASICs, or FPGAs, field programmable gate arrays. I think you might have heard of this kind of dedicated hardware devices, right? And on the other hand, they could be meant for our regular PCs, a general purpose software, like a general purpose software. And on the other hand, they could be meant for some embedded system. Hence, again, they may be resource constrained. So keeping all this in mind, we have to have the idea of what lightweightness means. How can we measure it? Can we measure it at all? Can we tell that this is this much lightweight and that is that much lightweight? Because if we can't, then how do we compare? If given two options, how do you compare that this is better than that in terms of lightweightness, or in terms of keeping lightweightness in mind? Which one is better? So to answer that question, we need to understand certain aspects of how we quantify lightweightness. And this starts from the first one. It's called area. So what this is area? Area kahan se aaya, right? So area basically refers to the chip area. When you talk about area, we're actually talking about the chip area. So why the chip area? Now see, generally when we manufacture these devices, and we are having some algorithm, right? And we are manufacturing a device, and that algorithm will sit in that device, right? So it has to be there. So we have to understand what is the available area on the device. If our whatever circuit we have designed, if its area becomes more than what is available, then it becomes unusable. And that is the major problem, because for lightweight devices like RFID tags, they are severely constrained. They will have only a couple of thousand gates to realize some logic. Hence, it is going to be very, very tough for you to fit some conventional algorithm inside it. Okay, so that is a major problem that we want to face. We will be facing. Hence, area is a fundamental requirement. Okay, in lightweight crypto. So going further in this direction. Okay, how do we? So we have talked about, right? How do we measure? How do you quantify lightweightness? No, just telling area doesn't matter, right? How will you quantify? So there are certain notions. For example, when we Cipher, estimate its hardware. What is the hardware? And gates 200, 35 NAND gates, maybe 50. Okay, this is maybe your requirement. Just hypothetical cipher. So, and then we have a second cipher, which requires 5 XORs, 12 AND gates, 59 XOR gates, 31 buffers, XNORs maybe. How do you compare them, right? This is like comparing apples and oranges. But there is something you can compare them actually. There is an idea, there is a normalization that you can. So the first thing that you have to be careful about is what the technology in which you are going to implement them. Now, when we talk about this technology, basically what we are trying to mention is what is the chip manufacturing technology, because ultimately we are going to manufacture some chip out of it, maybe some ASIC will manufacture. So what technology behind it? So generally you might have heard that this, in smart advertisements, they come, okay, micron technology, this is that technology, this, that, 8 nanometer. Nowadays it's a buzz. Apple has launched an 8 nanometer processor, right? Now Samsung has also launched some 8 nanometer processor. So this technology is very important. In which technology you are coming in. So when we compare two things, we cannot compare the 8 nanometer technology with the 20 nanometer technology. It's not comparable. We have to compare them on the same ground, on the same technology. Now what happens is, these designers, they have certain tools where they implement these algorithms, and they use some hardware description languages. So for example, Verilog or VHDL, these are hardware description languages. And in these languages, they write the code of the cryptographic algorithm they are designing, and then they pass it on to a tool. And that tool will analyze this and give them what is known as a synthesized netlist. So that netlist actually gives them the actual gates that they will need. Okay, in that particular technology. So they'll map it to that particular technology. For example, if it is 8 nanometer technology, the tool will be given the necessary libraries for that technology, and they will synthesize this netlist, and from that we can estimate what is the area. Okay, by counting the total area and then doing a normalization. And what is this normalization? Basically, what you do is that you add up all the areas of different gates. For example, there is one AND gate. There is 2, 3 XOR gates. Now, every gate will have its own area. Okay, maybe it's a nanometer square. In nanometer square unit, it has got some area. This is defined in the library. The library has all the information. The library is like a collection of all the gates, the specifications of all the gates, their power consumption, their area, and many other things. Okay, there are a lot of other things in the library that is there, and from there, this information that you get this much, what should I say, this many gates, you add up and you get a total area in maybe nanometer square. Now what you do is that you divide that area by the area taken by a 2-input NAND gate. So a 2-input NAND gate is the unit by which you divide the total area. Okay, and then whatever you get, you call it as a GE, gate equivalent. So if you have total area is 100 and gate equivalent area of one NAND gate is 2, then you divide 100 by 2, you get 50 gate equivalent, 50 GE. That is the unit. Gate equivalent is the unit of that area. Okay, now you can easily compare, take two ciphers, do their analysis, get this total area, divide it by the area of an AND gate, whatever GE you get, you can compare. If one cipher has 100 GE, another cipher has 50 GE, then definitely the 50 GE cipher is more efficient in terms of area. But only in area, we are not commenting about other features of the cipher, only for area. So try to understand this. So this is the notion of how area can be used to quantify lightweightness. So you can compare ciphers by this area, right? Now, what comes, what else can you do from there? See, now, one thing is very important. You should not compare different technologies. You can compute this area in different technologies like 8 nanometer, 80 nanometer, you go to higher 180 nanometer, lower, I think now 8 nanometer is the lowest that you have. So you can actually do it in various nanometers, but when you compare, you must normalize them in the same technology. Okay, so that is very important. So this, herein comes the idea of area. Now you can understand, when you are constrained by a device, when you need lightweightness, area is one of the major features that we should have. We should have some idea that whatever cipher we make, it should fit in within 1 kilo GE, 1000 GE, 1 kilo G, 1 kg. That could be our criteria. And then we can design the cipher, we can optimize it, we can try to play around it and see if it can fit there, right? So this is the idea of area. Next comes power. So as I mentioned, we can also compute power, and according to various technologies, this power will change. So if you have 8 nanometer technology, different power consumption. If you have 80 nanometer technology, different power consumption. So based on what is the technology, CMOS technology, this power consumption will change. Like area, you can also compare the power consumption, and the tool can give you this report, that because the tool also has, along with the area of every gate, it also has the power consumption of every gate. That information is there with the library. So it can retrieve it, calculate, make some calculations. It's not like simple addition. It will make some calculations and give you the report that this is the area, this is the power that is consumed. And then this power can be in general also. You can have this power available to you in the form of information from the library. So the library can tell that the power is 1 microwatt per gate. So per gate or per GE, per gate equivalent, it is 1 microwatt. So if you have 1000 GE, then you multiply it by 1000. That's it. That is how calculate power. Now you can compare the power consumption profiles of different ciphers in a similar way, but in the same technology. So that is the only restriction. So this is how you can quantify lightweightness in terms of power consumption. Now, in certain scenarios, like I mentioned, that there can be a sensor in the ocean measuring ocean temperature or measuring tidal, the nature of tides. When is the tide coming every day? It can measure some kind of information, or what is the height of a wave. This kind of information it can measure. So it is resource constraint because in the ocean, I can't go and change its battery every day. It may be solar powered. Hence, if there is an overcast, it may not get charged. So we cannot have a very high power algorithm running there. It will run out of battery. So power consumption makes a sense here, right? Understanding power consumptions makes some sense there. So this is how power comes into the picture. Then we have latency. I think all of you know about what latency is. So you measure how many cycles you are consuming. Okay. Per block size. So for example, if you are consuming, it could be like, you know, this many, you have consumed 100 CPU cycles to process 1 byte. Like an example, 100 CPU cycles for 1 byte, right? So that is how what you can measure. So this latency also comes in the picture because latency affects throughput, right? So in certain contexts, you might be interested in throughput also. So it can be less, it can be more, depending on what is your requirement. You may want that I am interested in throughput of 1 Mbps at this much area with this power. This kind of things you can tell, right? And you can see which algorithm fits that best and choose it, right? In terms of, if you have a choice in terms of lightweight algorithms. Similarly, as I mentioned, throughput will come into the picture. We also know what throughput is. So how many, you know, the rate at which you process information. So you can measure it in Mbps or Gbps, right? Maybe you are having 2 Gbps, that is you are able to process 2 gigabits per second, right? So this kind of analysis you can do, and depends on the latency. And we know that all actually relate to each other, right? If your throughput is too high, what it will mention, what is going to be your power consumption profile, all those things will come into the picture, right? Like throughput, you have energy. So there is a unit to measure energy also. Okay, and I will tell you in the next slide. So how the way we are trying to compute throughput, how the similar way we are also able to compute the energy consumption of it. So we can measure them in something like picojoules. Okay, of course it relies on the power consumption profile and the throughput. So I'll share a formula with you just in the next slide. So after energy, we have efficiency. Okay, efficiency also comes in this in units. It's a derived parameter, but it is represented with respect to this energy, latency, and all those things, power and everything. So what is the efficiency? You can compare ciphers in terms of efficiency also. And going in this way, another very important lightweight parameter that we have that helps in quantifying lightweightness is the code size. Now you may ask, what is this code size? So actually this is more from the software perspective. So see, whenever you design this cipher and you will execute it in some software environment, like maybe in a IoT device in some restricted environment, you are going to work with it. That time what will happen is you must ensure that the code size that is required at the time of execution, it is able to fit in the memory that is available on the device, right? Otherwise, how will you run it? You will not be able to run it. So the device memory consumption should take care of the fact that what is the code size of that particular cipher that you are running, right? Because it has to be in the memory while it is getting executed. So the code size is also a very, very important part that it plays in quantifying lightweightness. Now, during the recent competition that is going on, NIST actually gave out some guidelines about what they are looking out for in terms of various of these parameters and what they are looking for in the next competition, in the next generation of lightweight ciphers that would be there, right? And this picture, this entire slide here gives you an idea about how we can quantify this notion of lightweightness and hence are able to compare between various ciphers when it comes to choosing something, right? So this gives us a fair idea about this notion of lightweightness. Now, as I mentioned, I'll tell you about the this energy and efficiency. These are the typical formulas that we have. In general, for lightweight ciphers, parameters are evaluated at 100 kilohertz frequency. That is the general frequency considered, because a lightweight device is not supposed to run on very high frequencies, because it will run out of power if it runs on so high frequency. In general, the basic rule of thumb, it is not that it is absolute, it's a rule of thumb that we evaluate various parameters at 100 kilohertz frequency. Okay. As I mentioned, area and power depend on the CMOS technology, because it is a factor, it's a function of that CMOS technology. And then you have this energy. As I mentioned, energy is computed in this microjoules here. So what you have latency, which is computed in cycles per block, and power, which is computed by microwatt per block size in bits. Okay, this is how power is computed. This will be given to you by the library you are using to measure, and latency you have to calculate yourself. And efficiency, that is hardware efficiency, this is how you calculate it. It's throughput. You remember throughput you mentioned, like kbps, kilobits per second, per kilo gate equivalent, per complexity. This is the area complexity. This is the area. Kg is the area. So per kilo gate equivalent. So these are the typical ways you can measure this kind of lightweight parameters. These hardware performance metrics. They are also referred as hardware performance metrics. This is how you refer, right? So this gives you a rough perspective about how things are. But having said that, this is a very important slide, because it tells us that lightweight cryptography is not a single problem. It's a multi-dimensional problem, because you have many things to optimize. You have to choose between low cost and performance. At the same time, also choose the security that you want to provide, because these things are related. If you reduce the cost too much, it might happen that your security is getting compromised because you cannot afford to have the better security, right? And this security can be both from physical and algorithmic perspectives, both the perspectives. As you mentioned, cost is in terms of area or power, something like that, and performance in terms of throughput and energy. Now, if you reduce the cost too much, then maybe your performance can suffer, right? So these are the various type of things that you have to think about, right? So in terms of lot of dimensions that it has, you have to choose. It's like a trade-off that you do. So when you design a cipher, you propose a new cipher, you have to take care of all these things. Sometimes you will give that at this security, this much, this is the power consumption. At this security, this much, this is the power consumption, this is the throughput, this is the energy. Like this, you can measure. You can give different configurations of your cipher, uh, suited for different applications, maybe. Right? This is also possible. So it is very important to understand that lightweight cryptography is actually not a single problem. It's a multi-dimensional problem which has different verticals in terms of cost optimization, in terms of security level, and in terms of the performance that it gives, right? So you have to strike a balance between all of them, keeping in mind that what is your priority. For example, a smart bulb may not keep information that is useful beyond a particular time. Okay. So for example, if you change your password every 5 days, then a attacker has only 5 days to crack that password, right? Now, if you can give a considerable amount of security that makes it difficult for a attacker to break it within 5 days, then it's enough. You don't need astronomical level of security where you will not be able to break it even in 200 years, right? So you can strike a compromise, you can strike a balance there. So that is possible, actually. This thing is possible. So the next thing that actually comes into the picture is in terms of standardization efforts that have taken. Okay.
Excuse me, sir.
Yes, yes. Any question?
Yes, sir. Sir, here we consider the privacy or scalability?
You are considering?
Privacy or scalability in previous slide.
Previous slide. Okay, previous
Yeah.
slide. I'm going to the previous slide. Yeah.
So can you consider here the scalability?
Scalability?
Means here you have considered security, low cost and performance.
Right.
So can you consider here the scalability like the broader network?
Scalability, see, I'll tell you one thing. In this particular case, now, when you're talking about this cipher design here, but what do you mean by scalability? That is a fundamental question. It is not that you are deploying, if you can deploy one algorithm, if you can deploy one device, you can deploy thousands of devices because they're independent. So that won't come into the picture. The cipher's performance is not related to that, right?
Okay, sir.
Do you get my point?
Yes,
so,
sir.
If you are thinking about scalability from a different perspective, then I need to understand what is it. But if it is in this sense, then it doesn't affect us, right?
So sir,
Another thing could be scalability. Could be you are trying to increase the bit size, maybe. That comes under security then.
Yes, sir. So another one thing is that suppose this small devices kind of for mobile or some client.
Right.
So here, if we'll deploy a blockchain platform.
Right.
Okay. So the small devices, when the transaction will occur.
Right.
So like Bitcoin transactions or Bitcoin platforms.
Yes.
Then the huge scalability is like a transaction per second, TPS.
Right.
Right. So here, so many devices connected to each other.
Right.
So that time there so many transactions will occur. So all will perform the on-chain or in the blockchain. So here is the limitation means how to break or how to trade up between the scalability with.
That kind of scalability comes only in the application specific, right? You're talking about blockchain. You are limited by number of transactions or something. Now, of course, if you are talking about crypto mining, that is not possible on a lightweight device, right? You need dedicated hardware for that, like ASIC grids or something like that, which will compute millions of hashes per second. This is not meant for small devices. Generally, what is done is, if you have something that is too compute intensive, you outsource it, you delegate it. So if you are on the edge of a network and you have some difficult thing to do, you don't do it there. You send it back, get it done and get it back, because you are not capable of doing that thing. Okay, you get my point?
So excuse me, actually internet issue. So
oh, you couldn't hear me? I'll repeat.
Yes,
See,
yes, sir. Yes.
Yeah, what I am telling to ask, I'm trying to mention here is that when you are talking about the security of this device,
Yes, yes.
or for example, you are talking about some kind of blockchain application. So
Yes, yes.
here, if it is a compute intensive application, you will never do it on that resource constant device. You will delegate that task. So for example, you are on the edge of a network. You are at the sensor. You are a sensor. You are
Yes.
on the edge. Now, if there is a very difficult task that you have to do, you have to compute something very difficult. You might send the data back to the cloud, get it done, get it back. Okay, you can delegate that backside to the back of the network. That is possible.
Means outsourcing.
Right?
Outsourcing.
Yeah, you can delegate. You can outsource the computation
yes,
from yourself. So you can adapt like this. Okay, but when it comes in terms of security, this is not the setting. The security is how much is the how much you can tolerate, how much insecurity can you tolerate. So what I mean to say is that if you have 64-bit protection, that is not enough today. But if your data is only relevant for 5 seconds, then it is fine. If after 5 seconds, the data that you are trying to protect has no meaning, then you can use 64-bit technology there. You can use 64-bit security there. Right? So it depends on what is the level of security you can tolerate. That is what defines this point. Okay. So you see, if you try to bring in scalability in this picture, it will also come in one, it will fall in these 3 only. Okay. You can put it in performance, in the performance. Vertical.
Yes, sir. Yes, sir.
What is the good? What we're trying to achieve? Okay. In general, these algorithms have nothing to do in terms of scalability. You can scale them. You can deploy as many devices as you want. But it is important to know what you are trying to do with them. That is application specific. Now, if you are trying to aggregate 50,000 responses from 50,000 devices, can you tolerate it yourself? Can you aggregate 50,000 responses per second? That is the problem of the aggregator, not the problem of individual devices. So it's your answer is the answer to your question is application specific. What you are trying to do. Okay. And here we are talking about more of the bottom up approach. What is at the end node? What you are trying to do with a single thing? That is what we are trying to
Okay, sir. So like you are telling the resource constraint devices, what kind of computation or what kind of operation it will do?
So yeah, resource constant can be in any type. It can be in terms of, for example, it only operates at a very low frequency. That can be its resource constraint. It cannot operate at high frequencies. Its resource can be just the power. It can only consume. It will be if it operates at 100 kilohertz, it will only stay alive for 1 hour. This can be the resource constraint.
Yes, sir.
Okay, it can be anything. It can be anything. Maybe resource can be area. Maybe it can only, for example, RFID tags. Maybe it only has 200 gates inside. So any logic which requires greater than 200 gates is not realizable in the RFID tag.
Yes.
Okay, so it can be any of these.
Okay.
Okay.
Okay. Thank you, sir.
Yes. I also appreciate you asking the question. I encourage others also to stop me in between if you have any questions. So let's move on to this very interesting thing, that is the standardization efforts that is happening in lightweight cryptography. So actually lightweight cipher, lightweight crypto is very hot area now because people are trying to, look into it in a dedicated way. We need more focused ciphers that can solve the problems that we have in lightweight cryptography, solve the problem in resource constant devices. Now, in terms of standardization, there is already a standard, the ISO IEC 29192 standard that talks about lightweight cryptography, that talks about ciphers. It recommends for lightweight cryptography. In fact, in today's discussion, we are going to learn about the lightweight block cipher present, which is the ISO IEC standard, which is defined in this standard. Okay. Beyond this also, currently, this present is quite old. It was published in 2007, I guess. So it is quite old now. So we have the latest competition, which was announced in August 30, 2019. That is the NIST Lightweight Cryptography Standardization Competition. Okay. Oh, I think this is not August 30. This was the round 2. It was announced before. This was the round 2 announcement date. So it was announced before. I don't remember the exact date. But the NIST has been conducting this competition. Currently, it is in the final round. There are around, I think, 10 algorithms that are there in the final round of the NIST lightweight crypto competition. And nowadays, the standardization efforts are going on in this direction of to find the next standard for lightweight cryptography. Okay, so let's move on and look at the Indian standards. So these are the Indian standards on lightweight cryptography. This is the ISO. It's actually adopted from the international standard. They talk about this, that this is by the Bureau of Indian Standards. So information technology, security techniques, lightweight cryptography, part 1 general. And on the right hand side, you have information technology, security, lightweight cryptography, part 2 block ciphers. So these are the standards, part 1 and part 2, which conform to Indian standards. So India has adopted the ISO standard for its internal use. So if you are implementing some kind of lightweight cipher and you are implementing the one that is given in the standard, then you can get certification that you are conforming to the Indian standard. Okay. So this is the lightweight standard. Now we come into more of a theory. This is the second part of the talk where we go into a bit of theory of symmetric encryption and block cipher design in general. After that, we will look into two lightweight cipher constructions, how they are made. I'll try to keep this abstract. There is actually a lot of theory involved and we don't have that much time. So I'll try to give you some abstraction for which sometimes I have to skip some certain details. Okay. If anyone has any confusion, please ask me. So we are talking about block cipher design. Now this is a very favorite picture of mine to give what it means for block cipher and stream cipher. As you can see, a block cipher is the brick here in the wall, which tells us that it's a block cipher, while the pipeline here tells us about a stream cipher, which tells us that in block cipher there is a notion of a block, there is a unit of a block which it processes, while in case of stream ciphers, actually it is just the bit stream. So it is not no block size involved. Okay. Now we can just look into this nice slide which gives us the abstraction in more specific sense of construction, general construction. So what we have here is that in a stream cipher, generally we have something known as a bit stream generation algorithm, where we give a key as an input and it generates a bit stream. The encryption is very simple. It's like an XOR. So plain text is XOR with the key bit and you get the cipher text bit. The same thing is done at the decryption side. You regenerate the key stream. You use the key stream to XOR with the ciphertext and get back the plain text. Since XOR undoes itself, it's an involution. If you apply it twice, you get back the original thing, right? So this is the stream cipher thing. And in block cipher, actually, you have this notion of bits. So you process B bits at a time. So these B bits of plain text, you apply to the encryption algorithm, and then you have a key and you get the ciphertext of B bits. And the same thing you do just using the opposite algorithm, the decryption algorithm, where you apply B bits in the input, you have the ciphertext, and you apply it on the decryption algorithm and give the plain text back. So this is the key. And this is the key that you give the input, and the same thing is done. So this is the abstraction for block and stream. I think most of you are aware of the what should I say, setting. Next, let's look into block cipher. So we are not concerned about stream ciphers here. In today's discussion, we are actually interested about lightweight block cipher design, okay, or lightweight authenticated cipher design. So this is a typical what should I say, block diagram for a block cipher. You have the message, you have the key, and the output is the ciphertext, right? And the message and the key length can be different. Sometimes they're same. So here the message is of n bits, the key is of mod k bits, right? And the output is again of n bits. Okay. In general, given the key k, it's easy to encrypt and decrypt. So if the key is known, you can easily encrypt and decrypt. But if you are given a message and ciphertext, it is hard to compute the key from that, right? If you are given a message and ciphertext, you should not be able to get the key from there. That is the basic intention. Then we have the one-way property, that is with the key as the inversion trapdoor. What it means is that if the key is known, then you can invert it, right? If the key is known, then from the ciphertext you can get the message. And another thing is that the deterministic decryption. That means whatever you got from the encryption, if you apply the decryption algorithm, you should get back the original plain text. So here we have E of k M0 and we do a D of k of that and we get M0 back. So it's deterministic deterministic decryption, right? So this is the basic setting. I guess all of you should be able to recall this. And I guess maybe in the cryptography, initial cryptography session that you had, you might have learned about this. So now let's look inside, because in the lightweight cipher design, we have to see how this construction changes. That's why we should know what is the basic construction looks like. So if we go inside a block cipher, what is the structural aspect to it? Let's see. So basically, this is a very old notion from Shannon's very seminal and pioneering paper of communication theory of secrecy systems. So in this 1949 landmark paper, he actually gave this interesting idea of confusion and diffusion, which is still followed, right? So there are many interpretations, but if you are looking one by Massey, then it says that what is the confusion? Confusion actually complicates the relationship between the ciphertext and the plain text. That is what this confusion is all about, right? And if you look at diffusion, what it tells is that it spreads the plain text and the key in a way that it affects many digits of the ciphertext. So it talks about spreading the state, spreading the bits in the state. Every bit becomes related to every bit, right? They are related, they become related in the state of the cipher. That is what is diffusion. And confusion is it makes the relation complicated. Diffusion means it makes all of them related, and confusion makes that relation complicated. So that is what is important, because all of them should be related, because otherwise your cipher is not well diffused. It can have independent structures inside it, which is not welcome. On the other hand, confusion makes it relation complicated so that you are not able to break it easily. Okay, so both of them are needed. So block ciphers are designed to provide sufficient confusion and diffusion. That's very important, this word, sufficient. What do you mean by sufficient, right? How do you measure sufficiency? So how do you get this confusion and diffusion? Very basic idea is you get diffusion from permutation, or at the bit or the byte level. Simple permutation, and generally it's the linear component. So it's linear in nature. Okay. On the other hand, confusion comes from simple things like S-box. You might have heard of this, an S-box. S-box is nothing but a lookup table. For example, if I have a 4-bit S-box, it means that it's a lookup table of 4 bits. So 0 gaya to kya aayega, 1 gaya to kya aayega. It's like an array with the values in the index position as the output, and the index value itself as the input. So you keep, in the array, in the first position, it is 7. That means array of 0 is equal to 7, right? That means if 0 is the input to the S box, 7 is the output to the S box. So like this, it's a very simple lookup table, and it's a non-linear component of the cipher. So any block cipher you take, it contains some combination of S and P, some combination of substitution and permutation. Okay. Now, how they are exactly designed, that will vary from cipher to cipher. That is where we will try to see how lightweight ciphers try to design diffusion and confusion to use this to their benefit. That is what we are going to learn today. Okay. And then you have this idea of confusion and diffusion. I guess this is clear to all of you that confusion and diffusion allow us to make the relationship between the ciphertext, plain text, and the key. These 3 things that we have. Plain text is there, key is there, ciphertext. The relationship between them becomes complicated due to confusion, and they become related. All of them become related. All the bits become related to each other due to the diffusion property. Okay, so this is how this is the basic idea of constructing a block cipher. Now, if you look at a block cipher design, it is very typical. You will see that they have something known as a round function. What is a round function? It's like a simple core. It's a core of the cipher. There is a single function f, and you try to iterate that. You repeat that function. So like the figure given here, f is the round function, and you are applying f again and again. So p is the plain text. You are applying some k0, which is the key, and then you have the this f as the function, round function. You get the output, apply the key again apply f, apply the key again apply f. So this is the iterated way in which you keep on applying the this round function f, right? So this is how it happens. So keep on applying f, and after f, after every application of f, you apply the key. That is very important. The key is a secret, right? You all know. I guess you all know key is a secret, because I am assuming that the crypto class has already happened. So the design of this round function, see, whatever you are iterating, this is fine, but what is the core function that lies in the heart of block cipher design? How to design this core function? That is the basic idea of block cipher design, right? And another thing is, this core function may be weak, it may be vulnerable, but when you iterate it many times, it becomes strong. That is the idea of block cipher design. Actually, when you iterate it, then only it becomes stronger. Okay, so there are two ways in which you can design this. Using confusion diffusion, you can design the round function. One is known as the substitution permutation network, another is known as the Feastel network. These are the two ways. Let's see how they look. These are the two techniques. So block cipher design. So you have the SPN, the substitution permutation network, which is very simple. It is like you are applying substitution and permutation again and again. You have substitution layer, you have permutation layer, you have adding the key. Done. Again in next round, substitution layer, permutation layer, adding the key, and you repeat. And this is the key which is getting, it is an algorithm which generates a key for every round. So you use the intermediate key in this add key, again add key, you use the intermediate key, right? This is very simple SPN, substitution permutation network. Now, if I look at the other side, on the left hand side, what I have is the Feastel network. This is a bit different. What it does is that it splits the state. It splits the state into two halves. It can split it in other mechanisms also. Here we are considering that it is splitting it in two parts. So to one part, it applies this round function, which again can be of this nature. Okay, it can be of this nature. It applies the round function and then uses the other part to XOR with it and pass it on by swapping both the halves. Okay, this is very simple. It swaps, it split, apply, XOR, swap. Split, then split is also after swap, you apply, you XOR, again swap. Like this, you go on. And at the end, you just join. So this is the last part when you join this cipher text, right? So that's it. That's all you have to do. So this is the Feastel structure. Right? In today's lecture, we are interested about SPN. So AES, I think you might have heard about AES, the Advanced Encryption Standard, is an example of a classical SPN structure, while DES is an example of a Feastel structure. Okay, so this is both the examples of both schools of designs. Okay, now let's look at AES. I guess some of you might already know about AES. I am not going to describe AES here, but we will look at AES because of the historical perspective, because AES is the worldwide standard on a standard block cipher, but AES is not a lightweight block cipher. So we shall looking at AES so that later on when we look at a lightweight block cipher, we can understand what is the difference between them. Okay, so let's zoom in a bit. This is the AES structure. Let's zoom in a particular round. So what happens is you have the message. So for example, you have a 128-bit message. You separate the message into bytes. So you have 16 bytes. These empty circles are like bytes, 16 bytes. You then apply the key, you XOR the key. Then you apply the S box, which is a lookup table. In case of AES, the S box is 8 bits, right? You give 8-bit input, you get 8-bit output. So 8 cross 8. It's a 8-bit S box. So if it's an 8-bit S box, basically it has 2 to the 8 entries, right? For from 0 to 255. These are the 256 entries, and it will give some output for every entry. And it should give a unique output. Okay, it's a bijection. It should give it's a 1-to-1. It should give a unique output. So and then after that, what you do this operation is known as a shift row. You kind of swap these rows here and there, and finally you apply an operation known as mix columns, which kind of mixes the columns. It combines the columns together in some way, in an interesting way. Actually, I'll not go into the details, but this is how it happens. It operates on 32 bits at the same time using a matrix multiplication. It applies this mix columns. Okay, this is how it goes. K0, then you have K1, and you apply the keys in between. right? You apply these keys, K0, you're applying K1. So this is how the round repeats. So it's a typical structure, right? What are the things we have to remember? AES has 128 bits input, so split it into 16 bytes, apply the S box, apply the key XOR, you are XORing the key every time with all the bytes, you are XORing the key, and then apply the 8-bit S box. AES has a 8-bit S box. Apply the S box. After that, you permute. This is the shift row operation where you jumble up here and there. You put this to there, this to this. It's a permutation, byte permutation. And after that, you have a mixed columns which mixes the columns. And that completes the round. Okay, and then you start with the next round. So like this, every round you keep on continuing. So this is for us for the historical perspective. And how many rounds are there? We should be able to get it from this slide, which I have taken, I have borrowed it from Jeff Moser from his stick figure guide. So AES has 10 rounds. Now why 10 rounds? This is very important. And this has much to do with the lightweightness of a cipher. Hence I have put this slide here. Because the number of rounds that you keep for your cipher defines a lot of things. Okay. First of all, it defines what will be your latency, throughput, it depends on that. And also if you are like realizing the circuit in unrolled fashion, that is you put all the circuit at the same time, then it depends on the area, because area will increase with the number of rounds. So this has there's many things to do. In case of AES, when AES was designed, they knew that there was some attack up till 6 rounds, and they kept 4 rounds as security margin. This is very important. How do you decide the security margin? Okay, if you make the security margin too high, then your efficiency goes down. If you make the security margin too low, then you are vulnerable to attacks. You may become vulnerable to attacks. So you have to be very calculative there. You have to take a decision. It's a trade-off. It's a decision you take that how many rounds should be the security margin. In case of AES, for 10 rounds, for 128-bit AES, key size AES, it's 10 rounds. For 192-bit key size AES, it's 12 rounds. For 256-bit key size AES, it's 14 rounds. That is what the number of rounds are for the different variants of AES. Okay. So why I am telling you these things? Because when we look into our next cipher, we have to see how these things are going to affect us, how these things are going to change. And this is very important because the number of rounds actually have to be balanced. They cannot be too conservative, they cannot be too relaxed. Okay. And in either way, you lose something, either in terms of performance or security. So performance always comes at a cost, remember. So how do you do this security analysis? Basically, you explore different kinds of attacks. Of course, in today's talk, we are not going to look into attacks. We are looking into the design perspective. But these are some attacks I have shared with you here for your completeness of information. This is not exhaustive. It's a non-exhaustive list. So, for example, differential attack is very important. A linear attack is very important. Integral, related key attack, rebound attack, boomerang attack, algebraic attack, and their variants. There are a lot of variants. So differential attack is one of the most popular differential linear attack. Today, if you design any cipher, you have to show that your cipher is not prone to differential analysis, differential attack. What do you do in a differential attack? Basically, you try to study how differences propagate in a cipher. For example, you run the cipher with one input, you run it with another input, and then try to study how the difference of these inputs, by difference means the XOR, how the symmetric difference, there is XOR of these inputs, propagate through the entire state. This is what you try to find out from these various this differential analysis. Similarly, there is linear analysis. I'm not going to the details now, but differential is something we should know because in today's talk, we are going to do a bit of differential analysis. Some small part of it we will use. Okay, we are going to use. So let's see. Let's move on with our first case study. So the first case study is present. It's an international standard for lightweight block cipher. Hence, it's very important to study. So let's see how a lightweight block cipher has been made. Okay. So it was actually published in 2007 and it was designed to be particularly compact. So area was an important factor there. They wanted it to be compact. So they optimized it in terms of area. Now, as I mentioned you, that you have various kinds of lightweight performance metrics, right? Lightweight metrics like area, power, latency, throughput, energy, efficiency, code size, right? We all learned about this. So in their case, the designers wanted that the cipher should be compact. So their optimization metric was area. They wanted to design the cipher in such a way that the area should be as much less as possible. So if you can see, it was designed by 3 teams, one from DTU Denmark, another from Orange Labs France, and then Bochum University Germany. Okay, and it is one of the earliest. So you see, it was published in 2007. So it is one of the earliest design. That time, lightweight cryptography was not that prominent, but the designers were very clever and intelligent that they knew the requirement would come, and they designed it at that time only. Almost, you see, 14 years back, one Banvas, right? One Banvas back, they have designed it. So it's and it's prominent is one of the earliest examples of what is referred to as lightweight crypto. So let's see what present does. Okay. First of all, present is a substitution permutation network. We all know what a substitution permutation network is. We just discussed. It's a consecutive applications of substitution and permutation, right? So it's an example of a substitution permutation network. It's a 64-bit block cipher. Please try to understand this. AES was 128-bit, right? It's a 64-bit block cipher. So that is one primary thing that has been changed. So it's a 64-bit block cipher, and it has a 80 and 128-bit key. So it has 2 possibilities. One is it has an 80-bit key. Another possibility is it has a 128-bit key. So there are 2 possibilities, 80 and 128. Another thing is that it consists of 31 rounds. So try to compare with AES. AES had just 10 rounds, right? But it has 31 rounds. So why did they read so many rounds, right? What was the need? What was the necessity for so many rounds? That we have to understand. Okay. So this is the example of this diagram shows us the top level algorithmic representation of present. So you see, you take the plain text, right? You take the plain text, and after that you have this S box layer, and then the permutation layer, and you keep on applying it. And every time you update the key. That's it. You add the key, you have S box layer. So algorithm is very simple. You generate the round keys. There is a key. Every round has a different key. You generate the round keys from the master key, and learn the loop from 1 to 31 for all the 31 rounds. You add the key to the state. You apply the S box layer to the state. You apply the permutation layer to the state, and that's it. And you do it for 31. At the end, you add another key layer, right? So that's it. That's all you need to do for 31 round AES. Very simple description. Nothing complicated. No complicated stuff going on. No complicated mixed column operation, right? No complicated 8 bits. It is like 64 bits. That was 128 bits. It's smaller, right? So you can compare. Now this is the S box that present uses. If you remember, AES used 8-bit S box. Present uses 4-bit S box. So see, they have already made a decision there. A 8-bit S box consumes larger area, much larger area than a 4-bit S box. So they have compromised, they have chosen there not to use a 8-bit S box because they wanted to make it compact in hardware. So they have chosen a 4-bit S box in that place. Okay. And it uses 16 S boxes. You know, it's a 64-bit state. It uses 4-bit S box. So it has 64-bit state with 16 S boxes. 16 into 4 is 64. So it uses 16 S boxes. And you remember, in case of AES also, we had 16 S boxes because that was 16 into 8. Because one S box was 8 bits, right? So 16 into 8 was 128. Here it is 16 into 4 because 4-bit S box. So it's 64 bits. So, and this is the S box. As I mentioned, it's a lookup table. Agar 0 input hai, so C output hai, it's in hex. If 0 is input, C is output, 1 is input, 5 is output, 7 is input, then D is output, 8 is input, then 3 is output. Like this, if F is input, 2 is output. And remember, this is a bijection. There is no repetition. It's a unique one-to-one correspondence is there. So you exhaust all the possible 16 values, 0 to F. All the possible 16 values you exhaust and you give the output. So that is the S box layer, very simple, 4-bit. So you have already made a decision there to make it lightweight. Next is the permutation layer. This is the permutation layer. It is simple. It's a bit permutation. This bit will go to that bit. This bit will go to that. So it tells the 0th bit goes to the 0th bit. The first bit goes to the 16th bit. The second bit goes to the 32nd bit. The third bit goes to the 48th bit. Like this it goes on. And finally the 63rd bit goes to the 63rd bit. So that's it. It's a simple bit permutation. not a byte permutation like AES. AES had a byte permutation. It's a simple bit permutation, right? AES, in case of AES, the confusion was coming from the 8-bit S box and the diffusion was coming from the shift rows and the mixed column operation. In case of this present, the confusion is coming from the 4-bit S box and the diffusion is coming from the bit permutation layer. So bit permutation versus shift rows plus mixed columns. Of course, bit permutation wins. Bit permutation is much cheaper, right? So this is all there. This is the bit permutation. Very simple. It's connecting bits here and there. No computation involved. It is just connecting one bit to another bit. Just connecting this bit will go to that bit. That's it. That's as easy as that. It's one assignment basically in software. So bit permutation is clear. You can note the difference with AES. In case of AES, just compare this diagram with AES. AES, we had these 16 S boxes, and then we had this key XOR, and after that there was this shift row and mixed column. In place of shift row and mixed column, you have only a bit permutation. So you can already understand how present has made the design choice in such a way that they are better in area. They are area efficient. Area is one of the optimizing parameters, optimizing metrics here. So their construction is very simple. Only one S box and then a bit permutation. That's it. You have 16 S boxes you apply in one layer. There's the S box layer and then a bit permutation. And then repeat with the key XOR. That's all you have to do. So there is a key schedule also. So we generated the keys, right? The keys were being generated. You remember this update function? This update function was there. We are generating the keys for every round. So how do you generate them? This algorithm is very simple. So the user supplied key. So for example, this is for the 80-bit key. So the user supplied key is stored here, K0 to K79. At the ith round, the 64-bit round key Ki consists of 64 leftmost bits of the current contents of the register K. So what it does is that it takes the 64 leftmost bits. So from K0 to this kappa 0 to kappa 63, you are taking K16 to K79. That is the leftmost 64 bits from the register. You are taking and assigning to this state, right? And you are getting the round key. That's all. That's the substitution. And then how do you update? What is the update function? The update function is very simple. You rotate it. This is a rotation. You rotate it. And after that, you apply S box, the 4-bit S box to the most significant 4 bits. This is the S76, 76, 77, 78, 79. These are the most significant bits, 4 bits of the S box, right? And you get it and you apply it to the this what should I say, you replace it with this S box, single S box, right? And then you XOR it with some round counter. That's it. Round counter, you XOR it with the round counter value. What is the value of the round counter? So round counter goes from 1 to 31. So for every round, what is the value of that round counter? You XOR it with this. That's it. It's a very simple key schedule. I have not discussed AES key schedule, but if you guys know about AES key schedule is much more complicated than this. Okay. So this is another lightweight design decision. They have taken the lightweight key schedule. The key expansion algorithm or the key generation algorithm is very lightweight. It's very simple. That again adds to the lightweightness of this cipher. Okay. So I guess you understand this. Moving on is that what is the advantage we get from choosing a bit permutation for the P layer? See, just think about the hardware. In hardware, a bit permutation costs nothing. You just assign one wire to another wire. This connecting one wire to another wire. There is no hardware cost involved. This is wiring. There is no hardware cost involved. Hence, this is a very interesting point. This is an interesting design decision that the guys have taken. Now let's look into it details. I'll spend some time to look into these details of these design choices. What are these design choices that have been made, right? So this is a screenshot from the original paper. What they have written, let me quote. In achieving this, okay. So in this paper, we propose a new hardware optimized block cipher that has been carefully designed with area and power constraints uppermost in our mind. So area and power, they wanted to optimize. Yet at the same time, we have tried to avoid compromise in security. That is again, as I said, it's a multidimensional problem. You cannot optimize a single thing. Yes, yes. Any question? Is there a question?
No, sir, some noise background.
Okay, okay, fine. I'll continue. So, as I mentioned, that lightweight cryptography is a multi-dimensional problem. So, you cannot just go on optimizing something and forget something else. So, here they have optimized the area and power, but at the same time not compromising security. So, in doing so, what they did, they looked at some of the work that was done for the data encryption standard, right? And they worked something with the some of the features with AES finalist Serpent. So in AES competition, there were 5 finalists, out of which Rindal was chosen for AES. So from the AES finalist competition, there was the Cipher Serpent. They took some inspiration from there. Okay, and because Serpent was very good in hardware, so they took some inspiration from Serpent and took some inspiration from DES to design this, right? So what was their goal? The goal was Cipher is to be implemented in hardware. Remember, that is the goal. You cannot make a general purpose system here. It cannot be one size fits all solution. It has to be tailored for a particular solution. So that is the goal here. Cipher is to be implemented in hardware. So what they did, bit permutation, they decided bit permutation, we know it's free in hardware. There's no cost for bit permutation. Then there's S-box. They took 4-bit S-box, which is more compact in hardware than 8-bit S-box. It's much smaller. Right? And what else did they do? Let's go to the next slide. So here there are some equations. Don't get frightened by these. These are not complicated. I will not bore you with this. I'll just give you some idea of what it means. Okay. So since the bit permutation is there, bit permutation, see, AES had this mixed column matrix. AES had this shift rows. So AES diffusion was better, but the operations are complicated. In case of present, the diffusion is bad because the operation is too simple. The bit permutation doesn't have a good diffusion. It's simple. So we need something more along with the bit permutation. So what they did was they had some constraints for the S box that they selected. So they had some constraints. What was this constraint? The first constraint was that if the S box has an input X and another input as X plus del I is known as the input difference. Okay, X plus del I. So we are applying an input X to the S box. Another input we are applying X plus del I, where del I is the input difference. And then what is the output difference? Del O, because S of X is the output of the S box with input X. S of X plus del I is the output of S box for input X plus del I. And when I am taking the plus, means this XOR, actually XOR of them, I am getting a output difference. The output of this plus the output of this, right? And I am getting the output difference. So this is an equation. So here this line tells us that number of solutions for this equation should be less than 4. There should be less than equal to 4 such x's for which this equation is satisfied. Okay, for some input difference and output difference, del I and del O, right? This is I think this is understandable. Input difference, very simple. It is just some XOR. So for a 4-bit S box, you can have 16 differences from 0 to 15, right? These are the differences. Then the second point is for any non-zero input difference, again, for any some non-zero input difference, del I and del O, the Hamming weight of the input and output difference should be 1. If this is the case, there should be no solution for such a thing. Okay. Now this might look a bit complicated to you, but I will explain it to you. So see, what it means is that there is no input difference or output difference such that the Hamming weight of the input and output difference is equal to 1. That means you don't have any 1 Hamming weight input and output difference. Okay, now I'll explain it to you further using this diagram that will come. Before that, we should understand what is this difference distribution table. Now you remember what I said here, that the number of solutions to this should be less than 4. The difference distribution table is nothing but the entire crypto system, entire solutions for all possible del I and del O. So if I vary the input and vary the output, you know that the input and output are all 4 bits. So I have 4 bits to 4 bits. That is, I have a 16 cross 16 values. There are 16 possibilities for the input. There are 16 possibilities for the output. So I have a 16 cross 16 matrix. This is that 16 cross 16 matrix. Del I inputs possibilities are 0 to F. del O output possibilities are 0 to F, and I have got a 16 cross 16 matrix. This is that matrix, and del O and this the entry here. Every value that you see is the number of solutions of this equation. Okay, how many solutions you can get? The number of solutions for the equation should be less than 4. You see, this is what is here. You cannot find any entry which is greater than 4 except for this, because this is the 0 difference. If the input difference is 0, the output difference will always be 0. There is no question about that. Hence it is 16. But for any non-zero input and output difference, the maximum value you can see in this table is 4, right? This is known as the differential uniformity of an S box. The maximum value for a non-zero input output difference in a difference distribution table is known as the differential uniformity of that S box. Okay, so this is important because the equations that you saw here are related. So you can see that the present S box satisfies the first position. Now we'll discuss about the second equation. Let's see. So see, this we are coming back to this. So we know what is the difference distribution table. We know that the highest value for the non-zero input difference in the difference distribution table is known as the differential uniformity, and that is 4 here, which is as per the requirement given here. This is less than 4, right? Now what is the differential branch number? Again, very simple. What is the total Hamming weight of any non-zero input and output differences? That is the differential branch number. The least total Hamming weight of any non-zero different branch number is X, is at least X. So if any any S box has a difference X, has a differential branch number X, if any S box has a differential branch number X, then we know that the total Hamming weight for the input and output difference is at least X. Okay, so here that is what this equation tells us. This equation, what is it telling? That the Hamming weight of input and output is 1. That means the total Hamming weight is 2. Hamming weight of input is also 1. Hamming weight of output is also 1. That means the total Hamming weight is 2. And this equation tells that there is no such solution. That means there is no such input such that this solution, this is satisfied, because this set is empty set. This is an empty set. The solution is an empty set. That means differential branch number of present S box cannot be 2, because by this equation it doesn't satisfy it. The Hamming weight of input is 1, Hamming weight of output is 1, total Hamming weight is 2, right? So there is no solution for total Hamming weight 2. That means the least that we can have it is 3. 3 से कम नहीं हो सकता. 3 से कम होगा तो ये equation violate हो जाएगा, which is a requirement for present selection, S box selection. So the present designer selected an S box such that this condition is satisfied. So the differential branch number of present S box is 3, because it doesn't satisfy this equation. Okay, that means the least value X such that the total Hamming weight, such that we have the least value of the total input and output Hamming weight differences is 3. 3 से नीचे तो ये equation violate हो जाएगा. So minimum is 3. Okay, so take this as an example. Here the input is 4, right? What is the Hamming weight of the input? 1. Output is 1. Output difference is 1. This is the difference. Input difference is 4. Hamming weight of input difference is 1. Output difference is 1. So Hamming weight of output difference is also 1. Here it is different. What is 4 in binary? Hamming weight of 4 means what? 4 is 100. That is 4, right? 0100 in terms of 4 bits. 0100. That means Hamming weight is 1. Hamming weight is the number of ones in the binary expansion. If you don't know it already, Hamming weight is the number of ones in the binary expansion of the string, of the number. So here del I is the input difference. It's 4. So Hamming weight is 4. What is the output difference? Output difference del O is 1. Hamming weight of 1 means 0001. Hamming weight of 1 is 1. And then we have 5. 5 means 0101. So there are 2 ones. That is Hamming weight is 2. Hence the summation of input difference Hamming weight and output difference Hamming weight is 3. This is Hamming weight 3 example. This Hamming weight 2 example. So in case of present, such thing cannot happen. There cannot be a solution to this. That input difference is 4 and output difference is 1. This is not possible. But the right hand side is perhaps possible. Okay, so this is important. Try to understand that the differential branch number of present S box is 3. Differential branch number is the minimum weight of input difference and output difference for the S box. That is a differential branch number. Differential branch number. Okay, fine. So the above property implies that present S box is BN3. BN3 means branch number 3. Branch number 3 S box, right? Now, along with that, present has some other very interesting features. One feature is about the how the bytes spread, how the bits spread in the S box, various S boxes, how they spread across rounds, the diffusion, how the diffusion happens. There is an interesting property. I will show you some very nice diagrams which will help you understand this. So, first of all, try to understand there are 16 S boxes in case of present. We can group them. Group 1 is 4 S box, group 2 is this 4 S box, group 3 is this 4 S box, group 4 is this 4 S box. So we are grouping them. These are S box groups, right? This will help us to identify, to understand the properties. Okay, so we are dividing the 16 S boxes of AES into 4 groups, group 1, group 2, group 3, group 4, like this. Now, there are certain observations using the permutation layer. What is the observation? The input bits to an S box come from 4 distinct S boxes of the same group. Let's look them in detail. Observation 1. The input bits to an S box come from 4 distinct S boxes. इसका मतलब है एक S box का जो 4 इनपुट, जैसे 4 बिट S box तो 4 इनपुट है, एक S box का जो 4 इनपुट्स हैं वो 4 डिफरेंट S box से आएंगे. ठीक है, इस डायग्राम से थोड़ा मुश्किल हो रहा है. So I have made another diagram for you. This is the diagram which tells us. See, let us consider the first S box. Is S box का 4 inputs हैं? There are 4 inputs. Where are the inputs coming from? The first input is coming from this S box. The second input is coming from this S box. The third input is coming from this S box. Fourth input is coming from this S box. That is what the observation 1 tells us. The input bits to an S box come from 4 distinct S boxes of the same group. इसी group के हैं, right? These are all belonging to the same group. Remember the group. This is group. Which group is group 4? This is group 4. So these S boxes belong to group 4. And you can see they all come from the same S box group, right? This is important. Second is observation 2. The input bits to a group of 4 S boxes come from 16 different S boxes. इसका मतलब है यहाँ पर अगर 4 S boxes हैं, इनके जो inputs हैं वो 16 different S box से आएंगे. Again, इस पिक्चर से पता नहीं चल रहा है. I have made another picture for you. Just see this. These are the 4 different S boxes. This one, this one, this one, and this one. They belong to group 4, right? They belong to group 4. And you see, if I look at the inputs of this, they are coming from all the different S boxes there, right? All the different S boxes they are coming from. S box 1, 2, 3, 4, like this. They are coming from all different S boxes in the previous round. So this is what observation 2 tells us, right? That the inputs to this S box come from different S boxes from the previous round, from all the different 16 S boxes. And this is true for other also. I am showing you one example. This is true for others also. These are important points. These are important points. Okay. Next, observation 3 is the 4 output bits from a particular S box enter 4 distinct S boxes, each of which belong to a distinct group of S boxes. Right? Again, very interesting. इसका मतलब क्या है कि एक S box से जो output निकलता है वो different S box को जाएगा और वो जो different S box है वो different groups के होंगे. Let's see with the next diagram that I have made for you. Just see. S box इसका ये 4 output है. First output goes to this S box. This belongs to group 4. Second output goes to this S box. This belongs to group 3. Third output goes to this S box. This belongs to group 2. And the fourth output goes to this S box. This belongs to group 1. And this is true for other S boxes also. So again, we are confirming observation 3. The 4 output bits from a particular S box enter 4 distinct S boxes, each of which belong to a distinct group of S boxes in the subsequent round. Okay, so this is the idea of this observation. These are the observations, and they are actually helpful in the diffusion. They show us how the bits will spread, how the bits are going to spread in the state. That is how it shows us. Okay, this is the intuition. And the last observation, observation 4, is the output bits of S boxes in distinct groups go to distinct S boxes. That means if there is an output, there is an output bits of an S box which is a distinct, belongs to distinct groups, they will go to distinct S boxes, right? This observation is also very simple. I have taken here two S boxes. Okay, one is this S box which is given in red, another is this S box which is given in green. Just see that the output bits of this S box have gone here, 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 and here, while the output bit of this S box has gone here, here, in this S box, and in this S box is green, and in this S box, right? That means output bits of S boxes in distinct groups go to distinct S boxes, right? This is important. So these four observations are very central to the diffusion of present. How the diffusion spreads, how a difference spreads in the state. And this gives us an interesting theorem. I'll not prove this theorem here because this is not the venue and we don't have the time. So what it tells us that any 5-round differential characteristic of present has a minimum of 10 active S boxes. Now, what is a differential characteristic? Differential characteristic means how the difference is spreading over the state. So in the first round, there is a difference, how it spreads to the next round, how it spreads to the next round, how it spreads to the next round. And throughout all the rounds, how this difference spreads. Remember, in differential cryptography, I mentioned that we have these differences. We start with one input, we run the cipher, we have another input, we run the cipher, and we study how the difference between the inputs is spreading in the state. And here, these four observations lead to this theorem that any 5-round differential characteristic, that means if you have 5 rounds of present, they will have a minimum of 10 active S boxes. That means whatever trail you try to form, whatever intermediate path you try to make, you cannot have less than 10 S boxes that become active, right? So if you make some S box active, it will lead in the next round to some other S box getting activated. Like this, in 5 rounds, you have at least 10 active S boxes. And these 10 active S boxes is very important to decide how many rounds you will have to the cipher. So the decision on the number of rounds can be taken based on this kind of analysis. So in case of present, they knew that in 5 rounds, they can have 10 active S boxes. And building upon this observation, on this theorem, they decided that the security margin will be up till the total number of rounds is going to be 31 rounds. Okay, this is, so they have this extra thing. So every 10 rounds, so they have 10 active S boxes. Every 5 rounds, they have 10 active S boxes. Like this, they know this is how these S boxes go. And these S boxes are very active S box. Active S box means the S box whose input is non-zero difference. There's a non-zero difference in the input. So there's an active S box. So basically the difference is spreading in the state. That is what we are analyzing. The way the difference spreads, you have these active S boxes there. And these active S boxes help us in deciding what are the differential properties of the cipher for differential cryptanalysis. I'm not going into the details. I am being a bit abstract, but I just want to give you the idea so that you can go back and read further on these topics if you are interested. So this is the idea of this present, right? So this concludes our discussion on present. So what we saw that how designers took a decision of making the cipher lightweight by design. Okay, so they chose a smaller S box, they chose a bit permutation. Since they chose a bit permutation, they had to, and the bit permutation has slow diffusion, they had to make some other decisions, like they chose an S box that is BN3, differential branch number 3. That means the Hamming weight of an input difference plus the Hamming weight of output difference cannot be less than 3. It is minimum 3. They had to use this, and they had to use these 4 observations that we saw in terms of S box groups to make the cipher secure, because they did not want to compromise on security, though they want to optimize area and power. So these are the decisions they took to make the cipher secure. And the number of rounds they took was 31 based on these observations. Okay, so this is the idea. So now we move on to our second case study. The second cipher, it is GIFT. The cipher is called GIFT. Is again another lightweight cipher that improves upon present. It was proposed 10 years after present. In 2017, it was proposed. This is the first page of the paper. The title, I wanted to share with you that there are Indian authors actually. This Shubhadeep Banik and Sumit Kumar Pandey, they are Indian authors. They are from IIT Kolkata, who were actually part of at that time they were not at IIT, they were at different places. Okay, they are basically at NTU. So later on, before that they were in IIT. So that's why I wanted to share it with you. So see, what is the title of the cipher? It tells you the idea of lightweight. So gift is present, like present is also a gift. Present means you are gifting someone, right? So gift a small present towards reaching the limits of lightweight encryption. So they are optimizing further. How can you improve over present? That is the question. Okay. So now, what were the issues with present? One issue was that present has a BN3S box, which we learned, right? A BN3S box, branch number 3S box. Now, generally, in hardware, in chip area, BN3S boxes are costly in chip area. Okay, here we have an example, a comparison. Present S box, which is a BN3S box, costs 21.33 GE. GE stands for gate equivalent. The thing I taught you, how you measure the area. 21.33 GE. There is another cipher called Skinny. The S box of Skinny is BN2. BN2 means branch number 2. That means the Hamming weight of the input and the output non-zero differences is 2. It cannot be less than 2. It is 2. Okay. So, and that then its area is that 13.33 GE. That means there is a 10 GE difference, right? That is very, very large difference because you have 16 S boxes. So, if for 16 S boxes, you have 10 GE savings for every S box, then you get 160 GE savings. There is a huge saving, 160 gate equivalents you are saving. Okay. Another thing is also that present is actually weaker against linear cryptanalysis. I have not taught you linear cryptanalysis, but for completeness, I have tried to put it here. Present is weaker against linear cryptanalysis, so this has to be fixed. That is why gift came into the picture. Okay, this is the motivation. What is the motivation? Can we remove the restriction of BN3S box? So this is something the designers needed. Can the restriction of BN3S box removed? Is it possible to remove the restriction of BN3S box? So the idea was that when designing the cipher, we will design the bit permutation in conjunction to the S box properties. So S box है हमारे पास, S box हम लेंगे, उसके properties study करेंगे और bit permutation के जो properties है उसको S box के properties के साथ link कर देंगे. We'll link them together, right? Something like that we do, so that we can use a BN2S box, but still do better, still do good. Okay, so that's how gift came into the picture. So what are the advantages of gift? Gift has a smaller area thanks to the smaller S box. Okay, and it has lesser subkey additions. I will explain it to you what it means. Generally in AES, in case of present, you have seen the keys are added to the entire. Okay, there is a someone has raised a hand. Archana, Dr. Archana, you have any question? You seem to have raised your hand. Is there any question? Okay, maybe you have raised it.
No, I don't think so.
Yeah, maybe by mistake she has raised. So, so there is a smaller area because the S box is smaller. It's BN2 S box, not BN3, and it has lesser subkey addition. So, in case of present and AES, you have seen that the subkey additions are happening to the entire state. Every bit is being XORed, right? You have seen. But in case of gift, they have compromised there. They have not XORed it with every bit. They are saving XOR gates by not adding it to every bit. That is another lightweight optimization. Okay. Then it is better for linear cryptanalysis because of the bit permutation and the S box, which it doesn't concern you because I have not taught you linear cryptanalysis here. And then it has got lesser number of rounds. So we know that this has got 31 rounds, right? It has gift has lesser number of rounds than present, and hence its throughput is better because latency is less. So they have optimized in the number of rounds also. That is, they have reduced the security margin because of the analysis they could do, because of the construction that they made, right? So it has also even simpler and faster key schedule. Excuse me. So it is even a simpler. The key schedule is even simpler than present. Present is simpler than AES, and it is even simpler than present. Okay, that is interesting. So in case of gift, the versions are, there is gift 64 and gift 128. So 64 has 28 rounds with 64 block size. So you remember that present had 38 rounds, it has 3 rounds less. And for 120 and for gift 128, it is 40 rounds with a 128 bit key. So it has got 128 bit block size also. Present had only 64 bits. So it has got 128 also, 64 also. And both versions have 128 bit key size. Present had 80 bit key and 128, and this is only 128 bit key, right? So these are the differences. Let's look at the construction. Very simple, very similar to present, but there are certain differences. Again, we have 16 S boxes. It's a 4-bit S box. We have 16 S boxes, right? The permutation looks different from present, definitely. And then this key addition is there, and finally you go to the next round. Very simple construction. And here in key addition, you can see the key is not being added to all the bits. There are certain bits where the XOR gate is missing. This is done by design. So they are saving the XOR gate there. They are saving the XOR gate. Okay. So this is the 3 operations. First operation is called subcells. This is known as perm bits, and then this is add round key. Okay. So let's look at them. This is subcells. This is the S box of gift. It's a 4-bit S box, right? In present also we had a 4-bit S box. So it's a lookup table of 15 positions. So 0 to F, 16 positions, 0 to F, and these are the corresponding outputs of the lookup table, right? And then you have these 16 S boxes which you apply first. There is a first step. You apply these 16 S boxes, right? And then you have the perm bits operation. What is the perm bit operation? Basically, you have this permutation. Okay, this is a permutation. So pure bit permutation, like present has a bit permutation. So we know that present bit permutation is good because it is free in hardware. It's cheaper in hardware. So the designers of gift have not given away that advantage. They are adopting it. They have taken everything that present did and did better than that. Use something better than that. Okay. So they have used these perm bits. What is the next step? The next step is add round key. Okay. So add round key is very simple, but see, add round key is added only to 32 bits. Add 32-bit round key RK to the state. So out of these bits, only to these 32 bits, the red, see the red XORs, these are the places where the key is being XORed. See 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This black XOR is not for key addition. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So this black is not for key addition. Black is for something else. This is for the round key addition. Okay. So this is the important thing, right? So the round key you are expressing like this, and this is expressed at these positions, right? So this is another advantage that you get for gift. Gift is optimizing over present in terms of the construction by reducing the gate count further. Okay. So let me put this design rationale, the origin of gift actually. So the origin of gift, what are we talking about? See, we have talked about 2 lightweight ciphers right here. So how did they come about? And this is, I am taking it from the original paper. I am putting this verbatim from the original paper. So how did it start? It started with a casual remark. What was the remark? That can the present S box be replaced by something like a smaller S box, like the Piccolo. Piccolo is another cipher, the Piccolo S box. Okay. Because the Piccolo S box is very lightweight, so it will be extremely lightweight since the core cipher only has some S boxes and nothing else. Because you see, the present cipher has nothing. It has got only some S box and some gates for key addition. That's all. Nothing is there. This is a very, very lightweight cipher, right? So it will be extremely lightweight because there are only some S boxes and you are able to optimize the S box area. But the problem is when they tested it, we quickly tested it, but only to realize that the differential bounds become very low because S box does not have differential branch number of 3. So because the differential branch number was not 3, the differential properties degraded. They were bad. I am not going into what is the differential property because we don't have time to discuss, but just take my word that the differential property is degraded. They are not good. They are not good for the branch because the branch number was not 3. That's why they're not good. They're bad. The diffusion was not happening properly. Okay. So that is when we started analyzing the differential characteristics and study the interaction between the linear layer and the S box. So the linear layer is the permutation and the S box is the non-linear layer. Remember confusion diffusion we just read few moments back. Surprisingly found that by carefully crafting a linear layer based on the properties of the S box, we were able to achieve the same differential bound as present. Okay, so that is the idea. So they found that by carefully crafting the linear layer, so the linear layer can be crafted with the non-linear layer. You are designing them together, not independently. ऐसा नहीं है कि दो separately design करके combine कर रहे हैं, एक साथ design कर रहे हैं दोनों को. We are designing them together, and when we are able to design them together, what happens is we are able to design them in such a way that despite the branch number becoming less, not BN3, it is BN2, still the differential properties are as good as a BN3 S box like present. Okay, this is the crux of the design of the lightweight cipher, and they are trying to optimize the area further optimizing the area. Okay, so today's discussion we have concentrated on area optimization, right? So surprisingly, we found that by carefully crafting the linear layer based on the properties of the S box, we are able to achieve same differential bound as present without the constraint of differential branch number of 3. Right? This was the major optimization that they did. They could optimize that. They could relax that constraint of differential branch number being 3. Right? In addition, this result can also be applied to improve linear cryptanalysis. Again, it's fine. You don't know about it, but it improves the linear cryptanalysis resilience also, which was not there in present, and thus GIFT was born. That is how GIFT was created. Okay. So this is how this thing actually happens. Just give me one moment. Just one moment. Okay, so what we have is that you get the idea, right? How this GIFT has been designed. What is the motivation? The motivation is the S box, the design of the S box. S box looks very simple. It's a lookup table. It's like a permutation of 16 values, but it is one of the major central to the design of block ciphers. The design of S box is central to the design of block ciphers, central to the design of lightweight ciphers. Okay, and along with the S box, you are also designing the permutation layer, the diffusion and confusion coming from permutation and substitution. That is what we read, right? The basic design principle. We are getting confusion and diffusion from substitution and permutation. And how do you design the substitution permutation in a way so that we can extract more, lightweightness from there? We are making it more lightweight, making the area as less as possible, right? This is how they came about designing the GIFT cipher. So in today's GIFT, what are the things GIFT did above present? First thing GIFT did was they came up with a smaller S box BN2 in place of BN3. By smaller I mean the branch number is small, so hence we know that it is known that if the branch number is less, then that S box is lighter, that S box is smaller in area. So that thing they utilized. That was the first optimization. Second optimization was that they were not XORing the key to all the bits of the state. They were XORing it with half of the states. Only 32 bits they are XORing. There they saved XOR gates. Okay, and then they also have a very simple key schedule. That is how they saved over present. They did better than present. Okay, so this is how you are able to design another lightweight cipher. Okay, and these two lightweight ciphers are popular. Once there are more constructions, of course, our 2 hours or 1 hour lecture is not sufficient. You need much more, idea and much more breadth to cover. So that has to be done. So if you would like to summarize this, what did we learn today in this particular talk? We started out our introduction, right, with the idea of lightweight cryptography. Why do we need lightweight cryptography? What is the notion? What is the logic behind this kind of tailored cryptography. It's like a special case. It's a customized cryptography, customized for resource constraint settings, customized for environments where they can have a lot of restrictions in terms of area, power, throughput, latency. It can be anything, any of these parameters, performance metrics, right? And then we understood about these various performance metrics, area, throughput, efficiency, energy, how they can be quantified and how we can use them to compare various ciphers. We understood that. After that, we moved on to learn about the block cipher design philosophy. How do you design a block cipher? So you understood that the idea is to have a round function, which is very simple. And that round function is iterated many times to get a secure construction. And there are two ways of doing this round function, right? One is the substitution permutation network, another is the Feastel network. And we concentrated today on the substitution permutation network. What was the other thing that we had? The other thing we had was that how do you get the security? We understood that the Shannon's notion of confusion and diffusion. So confusion and diffusion are provided to make the relation between the ciphertext, the key and the plain text as complicated as possible and as dependent as possible. So everyone depends on everyone. That is the work of diffusion, and the dependence is very complicated. That is the work of confusion. How do we get confusion and diffusion? We get them through very standard constructions like substitution, an S-box, or a permutation like the AES mixed column shift rows, or a bit permutation like present and gift. This can be source of diffusion, right? And we also understand that diffusion, the diffusion component is a linear component, while the confusion component is a non-linear component. We understood this, right? And then we saw how AES works, how AES fits to this SPN philosophy. We saw the various operations of AES, the sub-bytes, which is a byte-based substitution. We saw what they say, the sub-bytes and the mixed columns, right? And then we saw about the other two ciphers, right? After mixed columns, shift rows we had for diffusion, and then the other two ciphers we saw were present. One was present. Present was our first attempt to a lightweight cipher design, and we saw how present got rid of the complicated components that were there in AES. It had a bit permutation which was free in hardware. It had a small S-box, 4-bit S-box in place of 8-bit S-box, right? And its entire construction was very simple, or just some 16 S-boxes, a permutation bit level, and then a key XOR. That's it, as simple as that. And the key schedule was also much simpler. And then finally, we saw that how we can even optimize above that and get gift. While analyzing when analyzing present, we learned about the two things, the S-box grouping and how this S-box provides diffusion. The groups provide diffusion based on those 4 observations. And also we saw that how the S-box properties are used to get the number of rounds to be 31. While gift gave us a gift of being even more flexible, even more constrained. It optimized the BN3, BN2 restriction and designed a new permutation, and also got a key addition, not to the entire state. That it became even more lightweight than present, right? So that is what we learned. And this here I share with you the finalists of the NIST lightweight competition. These are the finalists: ASCON, Elephant, Gift COFB. So Gift is there. Gift COFB, Grain is a stream cipher based, Grain 128, ISAP, Photon Beetle, okay, Romulus, Sparkle, and Tiny Jumbo and Zodiac. These are the finalists of the NIST competition, NIST LWC competition. Among these, I have had the opportunity to work on ASCON, Grain, and also on Tiny Jumbo for their analysis part. Okay, and a bit of on ISAP. So this is the idea. Now I would like to share with you something that we do here at IIT Bhilai, the Deciphered Lab. So basically, it's a group of enthusiasts who work in cryptography, and we have collaborators from various labs across India and also out abroad, like what you have shared here from ISI to Canada, and then also France and Warwick in UK. We have joint projects with IIT Delhi and CDEC Noida. We also work on this 5G security and development of India's indigenous secure USB device, USB dongle, that is we are currently developing. And in terms of our current focus, we are working on these areas: lightweight cryptography, then fault analysis attacks, automated cryptanalysis, and quantum cryptography. And this is a big picture of some of the students and collaborators who work with us in the lab. Okay, and we have positions. So if anyone is there, who would like to, is interested in the field of cryptography, you can write to us. So on this mail ID, get@d.ci.phd.red, this Decipher, and the same website is also there. You can look up this website. So there are internships and project associate positions, and of course regular MTech positions through the institute institute policy. So this, thank you very much to Liz for joining today and taking part in this talk. I hope I could give you some flavor of what lightweight cryptography means. This is a artistic image of our permanent campus, and these are the websites where you can reach us. Finally, I give you this picture, which concludes our lightweight crypto. It's from the same movie. So if we are able to pull off lightweight, this is what it should look like. Fine. Thank you very much, and thank you again for inviting me here on this venue. Thank you.
Thank you, sir. Thank you so much for your wonderful talk. Participants, any questions, anybody? So in the chat box, one question is.
Some question is there. Okay, let me see.
One question is there, sir. That is like, how do we simulate is there any simulator by which we can see the performance of lightweight ciphers?
Okay,
that
simulators. Okay.
Yeah.
So you see, you actually need some tools. Like there are tools like given by these vendors like Synopsys, Cadence, and Mentor Graphics. So you have these tools like Design Compiler, okay, and you have these tools like Leonardo Spectrum. Okay, this is by Mentor, and I think Cadence is also, Virtuoso is there. These kind of tools are available. These tools actually give us the, they help us designing these ciphers and find out what is their area, what is the power consumption, and then you can calculate the throughput, latency, all these things, parameters you can get, performance metrics you can get from there. So generally you design them in something like Verilog. For hardware, for software, you can use any standard programming language like C, Python, whatever you want, and you can measure the. For software, you measure like what is the cycles per byte, other kind of things. And there's another thing also for lightweight platforms. You can use some other kind of devices like. For microcontrollers, you have separate kind of environments that you use. For example, if you are using ATMega or AVR microcontrollers, you have separate compilers available for them, because you cannot use the regular C compilers to compile programs for them, because they are 8-bit or 16-bit microcontrollers that they will have. So there are separate tools available from the. So you can get them from ARM. ARM has this Kyle and other kind of tools, so you can get them from there, right?
Okay. And one more question, sir. That is a basic question only. Can you tell about SBox? So.
Yeah, what is the question? Okay, sir, can you tell about SBox? I mean, vector calculations. Okay, I don't understand what is vector calculation, but SBox is actually very simple. SBox is like a lookup table. It's very simple actually. So you can think of an SBox like an array. So an array, you define an array of 16 numbers and you post values in that array. Now these 16 numbers is all the numbers from 0 to 15. You put some permutation of them in that array. Now that is a SBox. So now when you query that array, for example, what is the output for 0? You just output array 0. Whatever is the value in array 0, that is the output for 0. So that's like a lookup table, right? It's a very simple thing. But in general, SBoxes are much complicated. So they have Boolean functions that they realize that, any function, lookup table can realize any function, right? So the lookup table actually realizes a Boolean function, and this Boolean function you can actually find out by analyzing the input-output using Carnot map or any other kind of tool like Quinn-McCleskey or Carnot map, any other kind of tool you can use to find out the Boolean function. There are tools like Sage. Sage you can use to find out any SBox's Boolean functions, the ANF form, the algebraic normal form, these kind of things you can find out from there.
Yeah. Thank you, sir. These are the only two questions.
Sir, one more.
Yeah, please ask.
Yes, sir. Thank you, sir.
Yes.
Dhiman sir, it's a wonderful session. Sir, here I have a question regarding FPGA board analysis, sir.
FPGA?
Board analysis.
Board, yes.
Yes. Sir, these lightweight computations, lightweight mechanisms are best fit for IoT related systems.
Right.
Sir, how better way we can deploy or we can run on top of this board FPGA board machines, and how better way we can get the outcome as compared with the other simulations and all, because you had mentioned performance analysis and all will be done through some simulations, no sir? How
See,
better way we can get it?
I'll tell you one thing. Yeah, everything is a simulation. You are not doing it on the actual hardware. But
Sir.
FPGA, any kind of FPGA tool you use, perhaps you are using Xilinx Vivado.
Sir,
Or
Vivado, sir. Yeah, Xilinx Vivado.
Vivado. So
Yes.
Vivado has the internal tools to report this, the area consumption in terms of LUTs. In FPGA, they will show you LUT count. What is the LUT count and what is the register count? Slice register and LUT. This an area analysis you can do after synthesis. Once in Vivado you do the synthesis. After that synthesis, you can do this area analysis. So all these reports are generated by the tool itself. So for lightweight ciphers, to compare lightweight ciphers, you can actually run the FPGA tool like Xilinx Vivado or Altium Designer. You know, these kind of tools you can use to run them on the tool itself, and they will give you the actual area, and power and other kind of metrics if you want. So the tool itself will help you. I hope you know that you can find this, right? Have you done this?
Yeah, I've just started, sir. I got.
I'll encourage you that you can look into the tool. The tool gives you. There are very nice ways to find out the maximum frequency, to find out what is the area consumption. There, after synthesis in Vivado, there is the synthesis report. Synthesis report you generate. Inside the synthesis report, you will find this detailed calculation. How many XOR gates it required, how many LUTs it required, how many adders it required, how many multipliers it required, everything it will give, detailed information.
Okay, sir. Thank you. I'll look into it. Thank you, sir.
Sir?
Yes.
So you said your current focus is on quantum cryptography.
Right.
So quantum cryptography, it especially requires a single photon sources. So what are the currently available single photon sources?
Now see, when we talk about quantum cryptography here, we are not actually working with actual quantum tools or hardware. It is mostly theoretical quantum cryptography. So we work with, basically these tensors and this matrix algebra and all those things. That is the thing. We are not working on the hardware level. It's more of the protocol level that we work on. So presently we are just exploring the area. We have not started research. We are learning, because the quantum computing model is different. So we are trying to learn the quantum computing model as of now, but we are not working on any particular kind of, what should I say? Hardware. We are using some simulators, like, perhaps you know about the IBM simulator that is there. You use this QSkit, right? You perhaps know about it, where you do these small programs you can write. You can assign various kinds of, gates, quantum gates and all those things. So this is what we do. I hope you understand this, the context.
Yes. Thank you.
Yeah.
Sir, one more question we have, that is, can you please highlight how to use cryptography in image processing? I mean, object detection.
Okay. I think that
I don't think it's your area of
research. It is not my area of research, but there is something known as visual cryptography, but I don't work in there. Okay, and there is also something known as steganography, which works with hiding information in images. Okay, that's another area, but I think I'm not the right person to answer that question.
Yeah. And
anyway,
one,
you can find out, how these things happen, perhaps through further discussions. We can find
and one more question, sir. How Whirlpool algorithm is different from AES? So these are Whirlpool one cipher is there, I think. I also don't remember.
What is the name? What is the cipher?
Whirlpool.
Whirlpool. Okay, Whirlpool. Yeah. Whirlpool is, I think, a hash function, right?
Yeah, I think so. It is a
Yes, sir. It's a hash function.
Yeah. AES is a block cipher, so you can't compare them, right? It's a hash function. Whirlpool is a hash function.
Sir, any other questions? Anybody?
Just 1 second. I'm getting a call.
Yeah. Anybody else? Any question? No. Okay. Okay, sir. You can stop sharing your screen.
Okay, I'll stop sharing them.
Okay, sir. Thank you, sir. Thank you for accepting our invitation and delivering such a nice talk. I think after listening to your talk, many of the participants will really start working on lightweight cipher design. Thank you,
I'm
sir.
very happy to know that.
Yes, sir. Thank you, sir.
Okay,
Thank you,
so
sir.
much. All the
Yeah.
best. Please
Thank you
teach
all.
subjects. Please teach cryptography in your colleges and everywhere. Spread the word. We should have more people working in cryptography and security. The
Yes, yes, sir.
country needs that workforce. Yeah.
Yeah.
Thank you very much. Bye, Sanjit. Take
Thank
care.
you, sir. I will talk to you, sir.
Yeah.
Okay. Okay. Thank you. Thank you, one and all. We will meet tomorrow.